Okay, so this is an example of using spherical harmonics to solve a linearized Poisson-Boltzmann equation. So we've used spherical harmonics in class as solutions to the Laplace equation, but they're not just limited to that, right? We can expand anything that is a partial differential equation with homogeneous boundary conditions. In this case, we still have a homogeneous partial differential equation, so in principle we might be able to find eigenfunctions of the operator del squared minus kappa squared, but we don't need to. We can just use the eigenfunctions of the Laplacian itself, expand this term, and we'll recover solutions as we go through. Okay, so our boundary condition, you will notice here, is one of the spherical harmonics. It's the PL0 term for L equals 1, and so that's going to really give us a nice hint as to what this expansion is going to look like for the final solution. And we just want to require that as we go out to infinity, this electrostatic field, the phi, is going to go to 0. Okay, so this is our Laplacian in spherical coordinates. I'm not even going to write out the surface spherical Laplacian term right here. I'm just going to assume that we know that this thing has eigenfunctions that are spherical harmonics. We showed that in a lecture the other day. Okay, so this is the surface Laplacian, and if we go through and we expand the solution in terms of these spherical harmonics, those are the YLMs, by symmetry we know we only need the YL zeros. There's no theta, no phi dependence in this boundary condition, so there should be none in the solution to this problem. So I can write psi as an expansion of R dependent coefficients. That's the R functions that are going to describe everything between the surface of my sphere and infinity, and these are the eigenfunctions, the YL0. Okay, so what happens when we act on this with the Laplacian? We get first the R-dependent terms in the Laplacian are going to leave the spherical harmonic part unchanged, but differentiate the R-dependent terms, and the terms that involve this surface spherical harmonic, or sorry, surface spherical Laplacian, are going to operate on the theta and phi dependence of our solution, which is the eigenfunctions, the spherical harmonics themselves. Okay, so that is what happens here, and just going through and using the fact that we know the eigenvalues for the spherical harmonics are these minus L times L plus 1, we now recover this equation, which can be simplified to this, and so that is del squared psi is just this expression right here. Now, we can plug this all back into our original PDE, and what we have on the left-hand side is this, which is proportional to YL0, and on the right-hand side we have another sum over the YL0. So this is going to be true for all theta, that is, I can change the value of theta in the spherical harmonic and have this still be true if the coefficients on both of the two sides of this equation are equal, right? Which says that we can now go through and write down an equation for the R dependence in our solution as 1 over R squared, derivative with respect to R squared dr, and then we have this term here, I have the kappa squared, that's my Debye length squared, and this is the eigenvalue of the spherical harmonics, and this is the R squared dependence in there, and the function that we want to find again. So RL is our unknown here, and we're going to go through and simplify this, and what we have is that this is this equation now. This looks almost like the spherical Bessel equation. In fact, if we allow the argument R to be a purely imaginary variable, that is to make a substitution x equals IR, then we can go through and use these transformations of variables. These are just using the chain rule, and we find by inserting those into the original differential equation that we recover what is in fact exactly the equation for the spherical Bessels. I'm going to have to move my, okay, so I had conflicting buttons there. A little bug in the caption software that I'm using. Okay, so the spherical Bessel solutions now should come out of this equation. This is the spherical Bessel equation, and these are the solutions. I should get the JL components and the in L components, right? So usually we think that we're going to keep these, but it's not so clear in this problem because we're thinking about the exterior behavior and not the interior behavior. Okay, so what do we have here? These J's are defined this way in terms of the Bessel functions. These are the regular Bessel functions, and they're just 1 over the square root of r multiplied by those. So if we go on and look at what happens when we take our boundary conditions, so we have a boundary condition at 1 that says that we have to have a cosine theta dependence. And that says that YL0 of cosine theta with L equals 1 is exactly this cosine of theta. And so all we're going to need is the J1 and the N1 terms, right? So we don't need a sum over all these different things. Here are the J0 and N0 expressions. We don't need those. The ones that we need are J1 and N1 of x, right? So this is these are exact expressions for the spherical Bessel functions in this case. And so now we can ask what happens to these expressions, these nice clean expressions in terms of sine and cosine for the spherical Bessels, when we plug in an imaginary argument for x. Remember that r was the real variable and x was equal to I times r. Okay, so now we're going to just use our usual expansions, do a power series expansion for sine and also for cosine, plug in Ix in there, and what we find is that that becomes, the sine Ix becomes I sine hyperbolic of x, and cosine Ix becomes cosine hyperbolic of x. And so here is the J1 and the N1 variables. These are now these are the spherical Bessel functions of order 1. We can now go through and write down simple expressions for them in terms of hyperbolic functions. And that's great, because now we recognize that sine and cosine, as they go off to infinity, look basically the same. Or sine and cosine hyperbolic look basically the same. And what we're looking for is a multiple, a linear combination of J1 and N1 that will give us a solution that satisfies this boundary condition that the solution has to go to 0 as we go out to infinity. Okay, so we're going to, of course, work with things that can be made to be real. If I multiply the first one by I recover some real valued function. You see that N1 of Ix is actually already real. And so now these things look very similar when we've written them in this form. And it should be easily done to mix and match them so that we end up with solutions that are obeying our boundary conditions. Okay, so to find a linear combination of these that decays to 0 is the question. We have N1 minus I J1 with arguments Ix, that is the r, basically. Ix is equal to r. And those come out to be e to the minus x over x times 1 plus 1 over x, right? So quite nice. This was a very simple solution, it turns out. And that can be written as psi of r and theta. This is a factor that needs to be determined so that it's consistent with the surface charge on the surface of this sphere. If you want to think of it as a charged surface problem, we are working on Poisson-Boltzmann equation. So, okay, so this is the expression for psi. You see here the theta dependence is all in the cosine, and this is this rather simple function of r, really, given all the things that are going on in this problem. So let's go through and find a. Sorry, I went a little bit too far. So if we go through and ask what does this normalization this coefficient a1 have to be, it is given by this expression, and so our final expression for psi is that psi naught parameter times this expression, this function of r, multiplied by cosine of theta. And we can ask, what does that look like at different values of the Debye length? So if we consider a case where the solution is salty, the Debye length becomes very short, and the double layer around this particle becomes very short, but still dipolar, right? And if we consider a case where we make the salt concentration basically go to 0, then the double layer becomes very long, and this dipole sort of dipolar charge distribution extends out into solution. And so I think that's it.